Hello everyone, my name is Rafael. I'm an electrical engineer, and in this video, we're gonna have a conversation about distributed energy resources, rate design and compensation. And to do so, I brought this file. Let's read and debate. Introduction. The traditional way of electricity delivery from large power plants of transmission and distribution lines to the customer is increasingly being challenged, in part due to the growth of DER and the changing technologies. DER are resources located on the distribution grid, often on or close to the customer's premises, and are capable of providing many services to the customer and the grid. New investments may be needed to effectuate the two-way flow of electricity. New ways of allowing the utility to recover its costs may be needed, and new assumptions regarding the forecasting of customer demand will be necessary to meet this challenge. Oh yes, before moving ahead and talking about the rate design associated with the ER, let's review some concepts related to the classical rate design process. It is important. Definition and purpose. Before going into the details of rate design modifications that may be needed due to the growth of DER, a foundation must be set related to the basic purposes for rate design and associated foundational principles. Additionally, a key component of understanding how rates are determined includes understanding costs and which costs a utility is allowed to recover by the regulator. Number one, let's see the rates. Rate design, the process of translating the revenue requirements of a utility into prices paid by customers, is often stated to be more art than science. While there is often agreement amongst parties to the rate setting process on the various goals and principles of the rate design, parties will value and weight those goals and principles differently. Furthermore, the parties' opinions on the specific application of those goals and principles will vary based on their application. Rate design may be influenced by legislative initiatives and political and environmental policies. However, a single rate design may not meet all rate design principles and policy goals. Indeed, many of the goals and the principles conflict with one another, and it's the job of the regulator to weigh these principles and goals and approve a rate design that best reflects the public interest as the regulator sees it. The basic purpose of rate design is to implement a set of rates for each rate class: residential, commercial, and industrial, that produces the revenues necessary to recover the cost of serving that rate class. Okay, guys, let's move on to costs. To create an appropriate rate, it is important to distinguish between fixed and variable costs. The question then for the regulator is how much of a utility costs should be considered fixed for the purpose of setting rates. To the extent that the regulators desire rates to be based on cost causative elements, the allocation of those costs is, or should be, on the basis of those cost causative elements. Different types of rate design. Here we are going to see the different types of rate design that have been historically used by regulators. Flat rates. Number one, flat rates. A flat rate design charges customers pay a unit of consumption at the same rate for all units of consumption. This rate is then uniformly applied to any user by a customer within that class. This rate structure, in combination with a monthly customer charge, is commonly used in designing rates for residential electric customers. Indeed, this is the most common form of residential rate design. Okay, as this file says, flat rates are the most common form of residential rate design for residential customers. On the other hand, recognizing that the cost of electricity varies throughout the day and by location, a flat rate may not reflect the actual cost to serve a customer in a given time period. A flat rate, a flat per unit rate tends to benefit low-use customers and poses some disadvantages to some customer classes, such as commercial and industrial customers with high load factors and high volumetric consumption. Flat rates do not require advanced metering infrastructure technology to implement. Okay, one of the characteristics that is peculiar of flat rates is that they do not require a smart meter. Okay, we don't need smart meters if we are using flat rates. However, if we are going to use another kind of rate, then we are going to use an advanced metering infrastructure, also known as smart meter. Now let's go to block rates. An increasing, inverted, or inclining block rate structure is designed to charge customers a high per unit rate as their usage increases over certain blocks within a billing cycle. For each block, there is a price for all electricity used within it, with the price increasing as a customer moves through the blocks over a billing period. One of the main purposes of an IBR is to send a conservation signal to customers and to incentivize energy efficiency and reduce consumption on the system. These types of block rates do not require advanced metering technology to implement. Okay, so block rates do not require advanced metering technology to implement. Also said, they do not require smart meters. Now let's see time variant rates. Time variant rates are designed to recognize differences in a utility's cost of service and marginal costs at different times, hour, day, or season. Okay, now things are getting interesting. Things are getting interesting here. They are designed to recognize differences in a utility's cost of service and marginal costs at different times. Generally, a TVR design charges customers a higher price during peak hours. That's interesting. Charges customers a higher price during peak hours and a lower price during off-peak hours. Now, things are getting interesting. A customer may increase savings under a TVR compared with a flat rate if that customer uses energy in response to the time variant price signals, such as shifting usage to lower cost periods or conservation. TVR requires a meter capable of measuring the time of a consumer's consumption. A time of use rate charges customers different prices according to a predetermined schedule of peak and off-peak hours and rates. Requires advanced metering technologies to fully function. Okay, this is what I want to speak with you about, a time of use rate. And this requires advanced metering technologies. A time of use rate, TOU rate, requires smart meters. Otherwise, it is not going to be effective. Another one, three-part rate demand charges. Because the utility system is built to serve peak loads, the cost of providing electricity at the peak hour is higher than during non-peak hours. Yes, we know that. Part of this reflects the increased cost of having sufficient infrastructure and the generation necessary to serve customers during peak demand times. To address the situation, another rate structure option is the three-part rate, which adds demand charge to the existing fixed charge and volumetric rate. The demand charge component usually reflects the cost to provide electricity at the peak hour of the month. Okay, very good. These are the ways utilities can charge customers. Now let's move ahead and continue saying the concepts and definitions behind understanding DERs and their purpose and how utilities are going to earn from DERs and how prosumers will earn their share. What are distributed energy resources? Here we are going to define distributed energy resources. You may not know it. I didn't know. I had to read it and other materials to get to know what the DER is. And here, this file is going to tell what distributed energy resources are, and you are going to have a definition for it. For the majority of its history, the electrical system has been composed of large centralized generation, not necessarily sited near customers, and connected to load through the bulk, high voltage transmission grid. That electricity then flows down to the lower voltage distribution grid and eventually to the customer. Now let's see some definitions provided by accredited and acclaimed institutions such as number one, Lawrence Berkeley National Laboratory. For this laboratory, the resources include clean and renewable distributed generation systems such as high-efficient combined heat and power and solar photovoltaic systems, distributed storage, demand response, and energy efficiency. For California Public Utilities Commission, distributed resources means distributed renewable generation resources, energy efficiency, energy storage, electric vehicles, and demand response technologies. For New York Public Service Commission, distributed energy resources can be classified into energy efficiency, demand response, and distributed generation. ADR can include, but is not limited to, energy efficiency, distributed generation, demand response, microgrids, energy storage, energy management system, and electric vehicles. For NARUC, a DER is a resource sited close to customers that can provide all or some of their immediate electric and power needs, and can also be used by the system to either reduce demand, such as energy efficiency, or provide supply to satisfy the energy capacity or ancillary service needs for distribution grid. The resources, if provide electricity or thermal energy, are small in scale, connected to distribution system, and close to load. Examples of different types of DER include solar photovoltaic, wind, combined heat and power, energy storage, demand response, electric vehicles, microgrids, and energy efficiency. Now let's talk about the types of DER technologies. You can see that it is going to be an extensive study about DERs that I'm bringing to you. And you are going to get to know everything possible about DERs. Types of DER technologies. Examples of the types of service envisioned by vendors and suppliers include microgrids, conservation voltage reduction, volt-var support, the potential to provide ancillary services, frequency ride-through, and locational ramping. Number one, solar PV systems. What is this? Have you ever heard about this? Maybe you have, maybe not. Let's see what this file speaks about. Solar PV systems use solar cells formed into solar panels to convert sunlight into electricity. Solar PV systems can be located on rooftops of homes or commercial and industrial buildings, or can be ground mounted. The PV systems can be used to meet the energy requirements for the home or building, or the energy from the system can be exported to the grid through the distribution system to be used by a nearby load. Due to technological advances, falling panel prices, and other policies, including favorable tax treatment, PV systems have become the fastest growing type of DER. This category also includes community solar gardens, which are solar installations that are larger both by available generation capacity and acreage, and allow customers that are unable or choose not to have rooftop solar PV to participate in a solar program. Regulators will need to create rules or tariffs regarding the size of the community solar gardens that are allowed to interconnect at an interconnection point. Number two, combined heat and power. What is this? What is combined heat and power? Let's see. CHP systems, also referred to as cogeneration, provides both electric power and heat from a single fuel source. A CHP system captures the heat and uses it from many other purposes, such as heating, cooling, domestic hot water, and industrial processes. CHP systems can use a diverse set of fuels to operate, including natural gas, biomass, coal, and processed wastes. CHP can achieve efficiencies of over 80% compared with 50% for conventional technologies. And now wind. Wind turbines. Wind energy. Distributed wind energy systems use wind energy to generate power and are commonly installed on residential, agricultural, commercial, industrial, and sometimes community sites. The systems vary in size. A turbine for a home can be as large as 10 kilowatt turbine, whereas a turbine for a manufacturing facility can be several megawatts. Distributed wind systems can be connected on the customer side of the meter to meet its energy needs, or directly to distribution to support grid operations or offset nearby loads. Distributed wind systems are often defined by technology application based on location relative to wind use and power distribution infrastructure, and not by size. Energy storage. Energy storage can be used as a resort to add stability, control, and reliability to the electric grid. However, given the recent decline in costs and technological improvement in storage, storage has become an option that is able to compete with many other resources. With the growth use of intermittent technologies such as wind and solar energy, energy storage technology can provide the needed power during periods of low generation from intermittent resources that will assist in keeping the electric grid stable and possibly prevent curtailment of resources in spring and fall months when electricity consumption is not affected by summer air conditioning or winter heating loads. Microgrids. Microgrids are localized grids that can disconnect from the traditional grid to operate independently. Microgrids can strengthen grid resilience and help mitigate grid disturbances because of their ability to continue operating while the main electric grid is down, thereby functioning as a grid resource for faster system response and recovery. By using local sources of energy to serve local loads, there is a reduction of energy losses in transmission and distribution, which further increase the efficiency of the grid. Demand response (DR) can be used as a resource by utilities and grid operators to balance supply and demand. The use of demand response as a resource can lower the cost of electricity in wholesale markets by avoiding the dispatch of more costly generation resources, which then could lead to lower retail rates. There are several options for customers to participate, including participating in a time-based rate in DR products such as time-of-use tariffs, CPP, variable peak pricing, RTP, or CPR. Energy efficiency. Energy efficiency can provide a transmission distribution benefit by allowing the utility to reduce or eliminate the need for upgrades or new equipment on the transmission distribution system. And now let's go to enabling technology, the enabling technology of distributed energy resources. The enabling technology, number one, advanced metering infrastructure, roughly said, smart meters. Advanced meters are capable of measuring consumption in 15-minute to 1 hour increments. The meters are connected to a communications network, which then transmits the consumption information to the utility's back office for billing. It is also now possible for customers to access that same amount of information instead of waiting for the monthly bill. Customers can log on to their utilities online portal and access the hourly usage information, typically on a 24-hour lag. An integral part of an AMI system is a communications network. That network allows the meter to communicate with the utility and can send information like consumption, but also receive messages like prices or demand response signals. This two-way flow of information means that the utility can provide customers with usage, price, and cost information over the course of the month rather than only once at the end of the month. AMI also often includes a second radio to support a home area network. The ham is capable of transmitting information including usage, voltage, and generation data to a router or other in-home display in as often as 8 seconds increments. This communication is supported by Zigbee IEEE 2030.5, which is a low-power communication standard. In-home displays or routers can connect to the customer's Wi-Fi networks and any other devices inside the customer's home that support Wi-Fi, including Wi-Fi-enabled thermostats. Lastly, AMI can not only connect consumption information about the premise, but can also collect generation data related to and on-site DERs such as solar production and voltage. By being able to collect this information, AMI can be used as a data source for distribution planning and operation, facilitate compensation of the ER for its generation, and assist customer adoption and participation in many other DER products and services. ADMS, DERMS. To support the adoption levels of the ER, utilities may seek additional infrastructure and technological support to assist in maintaining reliability and enhance resilience across the distribution grid. Two options to support that goal are advanced distribution management systems and distributed energy resource management systems. ADMS add levels of communication, intelligence, and visibility into distribution grid for distribution utility to better understand real-time conditions across its distribution service territory. ADMS provides utilities with several specific functions, such as automated fault location, isolation and service restoration, conservation voltage reduction, and volt VAR optimization. With higher levels of DER adoption, DERMS provide an additional set of tools in addition to an ADMS network. DERMS can allow the utility to dispatch resources both on the utility side and the customer side, forecast supply and demand conditions up to 24 or 48 hours in advance, to better integrate AMI data with other utility systems such as ADMS, outage management, and weather systems, and communicate with third-party aggregator systems. The RMS can also be used to support islanding and microgrid features, which may provide additional value to both the customer and the utility in certain times of need. Both DE DERMS and ADMS are suites of technologies solutions that can enable the distribution utility to better understand, plan, operate, and optimize the increase in amount of the ER showing up across a service territory. Now let's talk about smart inverters. Have you guys studied in college power power electronics? If you know power electronics, then you know what an inverter is. Let's see smart inverters. As with the availability of technology on the utility side, there are technology options also available to customers. One specific technology is a smart inverter. For solar PV installations, an inverter is necessary to switch electricity from direct current to alternating current. The grid, including the local distribution grid, uses AC power, so before electricity generated via a solar PV installation can be exported onto the grid, it must be changed into AC. So this is what an inverter does. It converts DC into AC. More recently, this inverter can now be outfitted with additional software that can accomplish additional services. For example, a smart inverter is capable of actively regulating the voltage of the solar PV's output. As clouds pass over a solar PV unit, the voltage can drop on the electricity that is exported onto the grid, causing drops in voltage at that location. To raise the voltage levels up, the transformer capacitor will step in and provide voltage support. Having a smart inverter addresses voltage drops before exporting the energy to the distribution grid is a value and service that can be provided by the customer, which can defer or avoid additional distribution upgrades. DER considerations, questions, and challenges. Now let's talk about These considerations and the challenges related to distributed energy resources, monitoring and adoption rates, the level and the place of adoption of the ERs in a system is important in the determination of what, if any, policy reforms are needed. Since all electrical systems are affected by the ER increases differently, before the jurisdiction embarks on the journey to implement substantive reforms due to the growth of the adoption, it should look closely at data, analysis, and studies from its particular service area before any such action are taken. Here, in addition to a path for regulators and utilities to plan for future utility and regulatory roles, we have included an adoption curve that points out the importance of three stages of activity: grid modernization, the integration, and distributed markets. Each stage is identified with two characteristics: adoption of the ER and installation of technology to support the ER development. The majority of jurisdictions are still located in stage one, where there is a low amount of the adoption and utility investments in grid modernization are still underway. The move into stage two occurs when the adoption reaches beyond about 5% of distribution grid peak loading system-wide. Stage three occurs when a high amount of the adoption occurs and the regulators construct a system to allow for multi-sided transactions to occur between the ER and the distribution utility, but also to and from customers. This means the development of policies to enable distribution level markets and determining the role of distribution utility into a market facilitator role. Now the costs. The economic pressures that the ER may put on the utility and non-the ER customers with being a rate class is one of the most challenging issues facing regulators today. These economic issues include revenue erosion and cost recovery issues, as well as interclass cost shifting appearing in traditional utility rate design. First, number one, revenue erosion. This is a problem that utilities will need to face. Let's see why it is. A majority of utility costs are not variable in the short term. Traditionally, most utilities take in most of their revenue through a flat volumetric charge coupled with a fixed or customer charge. This has been the simplest way to collect the revenue, but for historical metering technology and customer understanding, many businesses use a flat charge for their products or services to recover their costs, including fixed costs. For this type of rate design, revenue recovery is at risk from any reduction in usage revenue from customers' usage. The compensation that nets off a one-to-one credit for energy and distribution costs reduce the utility collected revenue at the retail rate while reducing the customer's bill by the same amount. This netting may not reduce any of the utility's costs, but can negatively affect its revenue collection, though the effect is different in vertically integrated jurisdictions versus restructured jurisdictions. This revenue erosion issue is what has brought many of the utilities to the table to discuss the ER issues and leads to the cost recovery and cost shifting issues discussed below. In considering alternative ways for utility to make up lost revenue, other revenue models may be available with changes to the utility business model. For example, in the New York reforming the energy vision proceeding, the New York Public Service Commission identified a set of examples of market-based services that could generate revenues for utilities. These include customer orientation via the online portal, data analysis, co-branding, transaction or platform access fees, optimization and scheduling services that add value to the ER, advertising, under services, finance and engineering services for microgrids, and enhanced power quality services. Cost recovery. Reducing the utility's opportunity to recover the amount of revenue needed to reach its authorized rate of return threatens its ability to recover its costs for operations of the system. This in turn may lead to arguments for regulated utilities that these utilities are riskier than others and thus are deserving of a high return on equity, which would increase rates to all customers of the utility. Many view the responsibility of utility rates as recovering the embedded cost of utilities assets, earning a fair return or profit on the same, and recovering the operations and maintenance expenses necessary for providing service. This cost recovery covers the dollars that the utility has already invested into the assets required to deliver and, if applicable, to generate the electricity for a safe, adequate, and reliable level of service. The actual costs to build, operate, and maintain an adequate distribution system are often viewed as being primarily driven by the number of customers served by the system or by demand, where there is the coincident peak demand, the on-time highest peak demand the system must accommodate, or the non-coincident peak demand, which is the customer's highest demand. Regardless of the drivers of cost, most utilities and demand regulators view the utility's short-term costs, especially for its distribution system, as fixed. Indeed, the rate-based and authorized revenue requirements are fixed by the state regulator during rate cases. This fixed amount is then allocated to the different classes before being divided amongst the billing determinants that decide an individual's bills. Subsequently, the ER can affect the cost of distribution, transmission, and generation assets. To use distribution as an example, under traditional rate making, a reduction in usage and thus revenue driven by the ER in a single year may lead to a little, if any, reduction of the cost of the system. The territory still has the same number of poles, wires, and other equipment, all with the same useful life. This is a simplification since utilities are not simply handed the money they spend on their systems, but illustrates the issue with recovering utility costs and the related risk faced by utilities. On the other hand, the ER can also, over the long term, avoid or defer the construction of new infrastructure, including generation facility and transmission lines, and assist and support meeting local reliability needs. Therefore, understanding whether the time frame being considered is short-term or long-term is important to determining whether the ER is truly affecting the ability of a utility to recover its costs. Now let's see cost shifting. The cost will shift to what or whom? Let's see. Cost shifting is another issue that may affect customers in the same rate class as customers that have adopted the ER. Cost shifting or subsidies is unavoidable in practical rate design, but regulators endeavor to mitigate these effects in the large context of the many, often conflicting rate design principles. The traditional response to a decrease in cost recovery certainty or to enact a reduction in revenue is for the utility to come back to the regulator to request a change in its revenue requirement or rate design or both. I have a video on my channel about revenue requirement. If you want to know more about this, the revenue requirement, you can browse my videos, and see what it is about. In the case of the ER, of the billing determinants are lowered to mitigate the pressure on revenue collection affected by lower sales. Thus, the decline in usage would effectively be shifted toward consumers when the billing determinants are reset to account for the decrease of revenue received from the DER customers. At a low level of adoption, this may be considered merely another imperfection in rate design, but at large levels of adoption, it can be problematic and represent large amounts of revenue being shifted to other non-DER customers in the same rate class. There may also be equity considerations to take into account. For example, if customers living in multi-family housing are in the same class as the AR customers and there are no DAR options available to multi-family customers since they do not generally own their property, a regulator must consider whether shifting additional cost recovery to customers that may not have a chance to participate in DAR is appropriate. In sum, under the traditional rate-making model and commonly used rate design, if the utility passes the relevant threshold of the adoption, the utility may face a significant intra-class cost shifting and erosion of revenue in the short run. If left unaddressed, the utility could face pressures in the long term that might prevent it from recovering its sunk costs, which are necessary to provide adequate service. Now let's see the benefits. Why is the ER beneficial? Let's try to solve this question to respond it. The challenge of acknowledging, identifying, quantifying, planning for, and optimizing the benefits of the ER can provide utilities and customers, both those with and without the ER, is an issue on par with identifying appropriate utility costs, as discussed above. Currently, in many jurisdictions, a customer with the ER that has DG or ancillary service attributes may realize savings beyond any avoided cost savings due to avoided energy usage. This is because a growing number of parties involved in the DER debate acknowledge DER can provide material benefits beyond use, just those involved by the customer behind whose meter the DER is cited inapplicable. In the case of EE, many jurisdictions already socialize some of the costs to lead to cost savings beneficial to the entire jurisdiction. Some jurisdictions, utilities researchers and advocates have also concluded or posited that responsible encouragement of other types of DER adoption leads to positive cost-benefit results. In this respect, when using the traditional model for rate design, which doesn't compensate for change or charge particular customers for producing particular benefits or costs for the grid except through the or EE programs, a regulator would be missing that portion of the cost benefit analysis for the ER. This is an issue only to the extent that a regulator wants to acknowledge, encourage, and optimize and benefit from the ER. At the very least,